lines are state of the art. Yeah.
I'll figure it out eventually.
Is that good enough for people? Okay, cool. All right. So we finished up last time working through some confidence interval calculation stuff. We talked about the library example. It's worked on that. We had also then had sort of this next one that we didn't get to. The idea being that who's familiar with Flynn effect? Can someone tell me what Flynn effect is? Anything?
Isn't it just with IQ, people like getting smarter, the test was not really
Yeah.
necessary?
Yeah, exactly, right? For some reason, and it's kind of mysterious, we don't know exactly why. But if I developed an IQ and standardized an IQ test in 1990, right? What we would find when I standardized it, on average, people in 1990 were scoring 100, right? But if I fail to update that, if I don't re-norm that, right? If I'm going through and it's 15 years later, and I take a look, and in 2005, I have a bunch of people go through and take that. The mean of that test isn't going to be 100. It's going to be slightly higher, right? So we see this drift that happens continually over time in terms of our cognitive achievement test. We don't know exactly why it is. It's a phenomenon that we've seen pretty consistently. So what we're interested in here, we got a researcher who's interested in this effect and wants to take a look at scores for a test that was standardized in 1980. And so what they do is they take 120 people and give them this exam from 1980 and have them take the exam. And what they find is that the sample of 120 had a mean of 107, a standard deviation of 12, right? Population mean in 1980 was 100, okay? And for our IQ test, what's mean standard deviation on our IQ test? Someone said, what is it?
100 is the mean and standard deviation is 15.
100 is the mean, standard deviation is 15, right? So here, we already have a mean that's higher, which would be consistent with the Flynn effect, and standard deviation is a little bit lower than what we would expect, right? So it looks like there might, absolute values are different, but what we want to do is go down through and calculate point estimate for the current population on the old test, 99% confidence interval, and then an interpretation on this confidence interval, okay? I posted this. Did people get a chance to go through, take a look at this example? Okay, just to run through this quickly, our point estimate for the population today is 107. That's easy, right? It's just the mean of our sample, right? We know that the actual population value for this 1980 test in people taking it today probably isn't exactly 107, but that's our best guess, right? If you put a gun in my head and said, what is the population mean? This is gonna be my best guess, right? But then what we wanna do is we wanna maybe calculate a confidence interval around that, right? Because I know that the population mean probably isn't identical to 107. I probably have some sampling error around that, right? And so what I wanna do is say, all right, this is my best guess, but what I'm looking at is wanting to provide maybe an upper lower bound for what that, based on the data that we've collected, what the true population mean might actually be. And this is where we calculate our confidence interval, right? So we take our standard error is our standard deviation divided by the square root of our sample size. And then we calculate our confidence interval, 1.07 plus or minus 2.58. Where did I get 2.58, Evelina? What's that?
The Z-score?
That's my Z-score. That's the Z-score that's associated with 99% confidence interval, right? This is 0.05 in one tail, 0.05 in the other tail, right? So this is my Z, and here's my standard error. Right here's my margin of error. I don't think I talked about that in class. But basically, your margin of error is like your confidence, your tolerance value here, right? We take 2.58, multiply it by 1.095, that gives us our margin of error. This is what we're adding or subtracting from the mean, right? Again, I think about this as like my tolerance. Here's my point estimate, here's my best guess, but here's the tolerance around that, right? And think about like a machine part. Well, it's supposed to be this size plus or minus this amount. gives us a little bit of wiggle room. So we calculate that, but then we take our margin of error plus or minus 107, gives us a confidence interval of 0.042 to 109.8. Okay. And then C was generate or provide an interpretation of our confidence interval. I went through, gave you a couple different examples. All these would be right. Again, as you're working through your interval estimates and providing interpretations on these, I would strongly encourage you to try and change it up, right? Go through, we had a slide back there, talked about different ways you can talk about confidence intervals. If you get stuck just saying the same rote stuff, the same stock phrase over and over again, it's gonna get boring for you, it's gonna seem really repetitive. You're probably not gonna understand interval estimates as much as you could, right? So here are a number of different ways we might make it or interpretations we might draw from this. Basically, it's the same thing. We're just saying it different ways. We could say plausible values for the average age or the average score on 1980's IQ test in the current population range from 104.2 to 109.8 based on the results of these data, right? So we're saying, based on these data, it seems like these could be reasonable or unrefuted values, right? Results suggest that values falling below 104.2 and above 109.8 not compatible with estimates for the average score on 1980's IQ test in this data. Right? We're sort of flipping this on its head. We're saying anything below this or anything above this wouldn't be compatible with the data we've collected here today. Right? You'd say results suggest an average score of 107 on the 1980s test in the current population of adults with estimates indicating a maximum error of estimation of 2.8 points. Right? We're just saying, we're letting you do the calculation on your own, right? You're saying about 107 plus or minus about 3 points, right? Again, this can be an effective way to communicate sort of the imprecision of our estimate for other people, right? So any of these would be good. And so as you're working through these, I encourage you to go through, play around with your language and how you're thinking about things. It's gonna help you think about these more flexibly and be able to use these a little more efficiently as you're working through stuff, okay? Now, in terms of thinking about general stuff, like what am I, as an investigator, taking from this? Would say, given what I know about IQ scores and the range and tests, plus or minus 3 points on an IQ score seems pretty precise to me, right? We've done a pretty nice job in terms of that. If I'm off, if my expected margin of error or my expected sampling error based on this is 3 points, I'm feeling pretty decent about that, right? Nick, what's going into my the precision of my estimate here? What's causing my estimate in this example to be pretty precise?
Yeah, well, the small margin of error makes it precise.
Right, and so what goes into determining that small margin of error?
Large sample size.
My large sample size, right? I had a big old number down here in the denominator, my standard error, right? And that large sample size drove that down. It led to a more precise estimate, okay? And in general, right, remember that we just didn't do this for the whole heck of it, right? We went through and calculated this because we had a question about the Flynn effect, right? And so we can say, based on this confidence interval that we've calculated, looks like we do have support for the Flynn effect. Given that 100, right, the average score when this measure was validated and standardized in 1980, is 100 a plausible value for the current population on this test? No, it's not. Why not, Haley?
It's not within our range.
It's not within my confidence interval, right? It's actually quite a ways outside my confidence interval, right? And so we would say that population average, today's population average score of 100 is not consistent with the data. It's not a plausible value. It's not saying it's impossible. You might have just gotten a weird sample, but it's generally saying that that's below what we would expect. And so in general, we can go through and say, probably conclude that, yeah, these data do provide evidence for the Flynn effect just because our sample of 100 is not in there, or point estimate of 100 doesn't fall within our confidence interval. Okay. So does this help kind of bring this together and sort of help in terms of thinking about interval estimates, how we might use them, draw inferences and things along those lines? Any questions? Okay. So another thing to think about in terms of our interval estimates.
I
Mm.
do have a question.
Mhm.
I was just waiting till you finish the interpretation
Okay.
section. Do you mind repeating margin of error and how to calculate that?
Yep, your margin of error is just, basically it's what you add or subtract to your point estimate. That's all your margin of error is, yeah. So it's just your confidence level, your statistic multiplied by your standard error, and it's just what you plus or minus from that. So margin of error, understanding margin of error will start to become important when you start working through that coming to pitch article. Basically, if this is your bar representing your mean, right? This is just your margin of error, plus or minus, right? That you write above or below that, right? Coming pitch will start talking about overlapping your margin of error. This is what they're talking about. So not the whole thing, right? But above, below, that's going to be your margin of error. For means-based analyses, the stuff that we're going to be working on until we get into confidence intervals on effect size, your margin of error is going to be balanced. Your point estimate's always going to fall in between when you're going to have tolerance above, tolerance below. When we get into effect sizes, distributions there are a little bit different, and so you generally have a shorter margin of error on the low end, a larger margin of error on the top end, but we'll talk about why that is at that time. Does that help out? Perfect. All right, so some additional things to keep in mind. So if this is drawing on a number line, for our age of books example, point estimate was, I can't remember, whatever it was, something a little bit below 24, and then our confidence intervals bound up above and below that, right? But if we go through and think about this as a distribution, right, the important thing to recognize is that our point estimate is still our best guess, right? We don't, sort of even within our confidence band, all values within the confidence band aren't of equal likelihood of sort of they're not all our best guess, right? Our point estimate is still our best guess. We're just saying that given sort of the confidence level that we're willing to accept, so this would be the low end, this would be the high end, right? So like any of our distributions, so something down here, so for the true age of the library books, it looks like it's just say 23.8 or something like that. 25 is still consistent with the data that we've collected based on the confidence level that we've created, but it's not as good a measure as 24.8, right? It's starting to get on the low end. Same thing, or starting to get on the high end. Same thing, something down here like say 22.6. It's still within the bounds of our confidence interval, but it's getting pretty less likely, right? It's right there on the edge. Our point estimate or something closer to that is still going to be a better guess, right? So think about this. Jeff Cumming talks about this as kind of like a cat eye type of thing, right? And think about it as a distribution above and below if you just wanted to sort of make that there. So here's our point estimate. That's our best guess. Here's what we're saying that goes above and below. But as we start to get on the margins of that interval estimate, those estimates as the likelihood of representing the true population value, at least based on the data that we've collected, start to get lower and lower, okay? Same thing here with our IQ scores. Our best guess is 107, right? Value of 109.5 is still within there, but it's not as good as guesses right here. Same thing on the bottom end, okay? So people kind of see what's going on with this. So it's not a clear demarcation like everything else. It's not that a value that falls, a tenth of a point outside my confidence interval is categorically different than something that's right on my lower bound limit, right? They're still pretty close. Technically, it's outside, right? But thinking about this the same way as we think about like p-values, right? P-value of 0.051. Yeah, it's not technically meeting our criterion for statistically significant, but it's probably not all that different than. So if you said, here's p.049 and here's 0.051, I wouldn't identify those as categorically different results. Okay. Questions about this? All right. So we can do this with a couple of different samples and start drawing inferences. Here, we have less than, I can't even say that right now. So basically it's a chemical in food. It's expected to improve memory. So we get 10 rats getting a normal diet that has lecithin, 7 rats, separate diet, no lecithin at all. Then we give the rats a memory test. I don't know what this looks like, but people who do this might. And we get for the sample that has lecithin in their diet, have a mean of 25, a variance of 61. The experimental group, or the experimental group that has no lecithin, a mean of 33, variance there. Wanting to go through, and researchers are interested in the estimating actual difference between the scores in these two populations, right? So again, 1 point estimate, 95% confidence interval, and then interpretations. So again, point estimates are just going to be our means. We go through, calculate confidence intervals for both of these. Why did I take the square root of the whole thing instead of just the denominator here? I mean, it'll,
Because it's the, you want the standard deviation, right now you have the variance?
yeah, right. So basically, we typically think about standard error being your standard deviation over square root of your n. But if I give you the variance, what's the relation of your variance to your standard deviation? Is variance of my standard deviation squared, right? So I can just take, if I have my variance here, oops, these two things are equivalent, right? It's just a little bit easier to run through and calculate. Again, the less times you have to go through and round stuff, the better off you'll be in terms of your estimate. So I give you variances, so you can just take your variance over your sample size and just take the square root of the whole thing. It's going to be the same thing. Or you can just take your variance, calculate the standard deviation, plug that in, and then take it over the square root of your sample size. Preference, right? They're going to be the same, but just want to make sure people aren't confused. But I made a mistake. Laura, did you catch my mistake here? Nice work there. Sort of miscopied my standard error into this, so correction on the confidence interval. But here, for our controls, these are this is confusing. So my control group is the rats that actually have lecithin. The no lecithin group is this one here. So those are kind of confusing. But my control group with lecithin, point estimate of 25, confidence interval running from 20 to close to 30. The rats without lecithin in their diet running point estimate of 33. Lower bound 28.5, upper bound 37.5-ish, okay? So go through an interpretation, or one interpretation you might come up with, might say population estimates for the average memory score of rats receiving standard amounts of lecithin in their diet range from 20.2 to 29.8, with point estimate in the sample of 25. Point estimates of memory in rats with no lecithin in the diet was 33. Plausible estimates of the actual population value ranging from 28.5 to 37.5. So again, even with this playing around a little bit, so we're not just saying the same thing over and over. But what's the big thing in terms of thinking about a research question that should be throwing bells and whistles and stuff all over the place? What do you think, Amanda?
What do you mean?
So I ran this study, again, not for my health, but because I thought that lecithin has an impact. We see that lecithin is proposed to be helpful in helping memory stuff, okay? So what did I find, what do at least these data suggest?
It appears that the confidence intervals, the point estimates that you're finding, the upper and lower limits, are fairly different from each other. So it does appear to have a gap, a significant gap between the control group and the non-control.
Okay, perfect. And this is the trap that you'll fall in quizzes, because you're absolutely right. It does look, based on this, it looks like there's a difference. But if you just tell me there's a difference, why are you going to lose points on your on your sets. What do you think by that?
You need to say why and what it means.
Okay, why and what it means, right? Am I happy with just odd difference? Like, hey, here you can take this thing and it might increase your risk of heart disease or decrease your risk of heart disease. It's just, hey, this thing changes your risk of heart disease. Am I excited about that? No, why not? Hey, what do I want to know?
I don't know what it means without any explanation. I mean, something could have a difference, but that doesn't mean it changes much, or,
Yeah.
I don't know, what can you do to?
Yeah, what do you think, Laura?
I think you're looking for the directionality of
Yeah,
the difference.
If I take this, is this going to increase? Do the cigarettes increase my chance of heart disease or reduce my chance of heart disease? That might be an important thing to know, right? And so, Kate, what's going on here that's hopefully you're catching on in terms of how we work through these this set or this problem? Based on these data, what impact does lecithin seem to have on memory?
It's in the opposite direction.
Yeah, right. So I mean, the whole idea, the whole reason we're doing this is that we're working under the assumption that lecithin improves memory. Well, we actually find something that's the exact opposite. Our control group that has normal levels of lecithin in their diet are scoring lower than our sample that has no lecithin in their diet. And it looks like based on the confidence intervals, they're a little bit of overlapping. But it looks like there could be a real difference here, right? It looks like it's in the opposite direction of what we would have expected. This is an important thing to note, right? We don't want to just say, yeah, there's a difference, and people will do it. I know, sort of that hoping this class will burn into your brain, you'll never forget it. It'll be like with you into old age. But I know that's not going to happen because we're going to have people going through sets and be like, oh, there was a difference, or there was a relation, or things along those lines. You have to tell me which direction that difference is. Is it consistent with the hypotheses? Is it not consistent with the hypotheses? And this is the trap that we can fall in if we just get too fixated on the numbers, and if there's a difference, sort of losing the forest for the trees, right? So in this question like this, I would want for sure you to say, yeah, it looks like there's a difference. Confidence intervals are overlapping a little bit, but based on rules of thumb like Cumming and Fitch, it looks like these are probably different, but they're different in the opposite direction than we'd expected. It actually looks like the rats who are receiving a special diet that doesn't have any lecithin in it, they're actually performing better when we'd expected them to be performing worse, right? So this is an important thing. Always keep this in the back of your mind when you go through, when you fill out when you complete a problem. Ask yourself, did I address the main hypotheses? So am I saying something about the research question at hand? One, this will make sure that you're not losing points needlessly on your problem sets, and two, it's just going to make you much sharper as you go through evaluating your own work and the work of others with stuff. Okay. So questions about construction of confidence intervals, kind of some of the stuff that we've gone through and talked about here.
I have a quick question relative to the problem 3 set. Is this how you want that question 12 constructed?
I would have to take a look at that, sort of what. So basically follow out sort of the steps of
These
sort of
steps.
how
Okay.
I've asked you to go through and do
Okay.
those. Okay. Other questions? All right, cool. Last thing, in general, think about guidelines for interpreting confidence intervals or comparing confidence intervals from a graphical standpoint. This is pulled from the Cumming and Fitch paper. This is a fantastic paper. Make sure you read this closely and understand some of the things that, some of the principles that they're talking about. Number one, we oftentimes won't see error bars on your bar graphs. And in this last set, people did a nice job of finding examples back. Hey, they didn't tell us what we need. Nice work. But even if people do put error bars on there, anybody read the Cumming and Fitch paper yet? Yeah.
I can't say that I understood all of it.
Okay, that's fine. What are the error bars that are typically put on bar graphs? Are they confidence intervals?
No, aren't they marginal error bars?
Yeah, they're standard error bars, right? Standard error bars are sort of basically this value, right? And the problem is that standard error doesn't tell us as much directly, right? Now, coming pitch says you can double that, and sort of that basically gives you a confidence interval, right? Or approximates a confidence interval. But why don't we just systematically include confidence intervals instead of standard errors? What do you think, John?
I think it's like one of the reasons it may not be like as compelling like data graph.
Yeah, but they don't look as good, right? Because our confidence intervals are larger than our standard errors. Standard errors oftentimes graphically end up looking small and makes me feel good about my graph, right? Well, my confidence interval is going to be probably larger, right? And so coming in you're saying you should always be working with just confidence intervals just because they provide more information. But wanting to go through and make sure that you understand what those error bars represent, whether or not they're standard errors or confidence intervals, making an interpretation of the means. What are the means that are actually being displayed? What are they, right? And then making an interpretation of the confidence intervals as we have before. And then this is helpful if we've got independent means, right? Making sure, and it's important that this isn't paired, this isn't before and after. This is group 1, this is group 2. But what Cumming and Fitch say is a general rule of thumb. When the margin of errors of your confidence intervals overlap no more than 50%, that's probably indicating a difference that's less than P, a difference that's consistent with P less than 0.05 probably, right? And so again, if I've got what I want to do, here if I've got this and this, right, and these are two different groups, what I want to do is I want to take the upper bound of my lower mean and the lower bound of my higher mean and look at this right here, this amount of overlap. And if that amount of overlap, sorry about that, Kate, I'll get out of your way. If that overlap is less than 50% of the average of your margin of errors, that's suggesting that, yeah, these two means are probably statistically different at P less than 0.05. Okay. Now this is assuming you got a reasonable sample size and that your samples are or your margin of errors are relatively similar. But this is a nice way of going through, even if authors aren't providing you all the information that you would maybe want, a way to go through an eyeball and say, well, if they didn't compare those two, can I assume that these are reliably different? I can use my confidence intervals in the overlap to start taking a look at some of that stuff. If the confidence intervals don't overlap at all, if the upper bound of my smaller mean doesn't even hit the same level as the lower bound of my larger mean, then we can interpret that as a statistically significant difference, P less than 0.01. But again, this is a nice way to go through, and you'll run into times when this starts to become helpful in determining sort of whether or not, making conclusions on whether or not things are reliably different or not. Yeah.
I'm just gonna repeat what you said to make sure I have it
Uh-huh.
right. When the overlap of the margin of error is greater than 50% of the mean, then it's statistically significant.
No, close. So when the margin of overlap, or when the overlap is less than 50% of the margin of error, right? Because again, we want these, the more a set of confidence intervals for two different groups overlaps, kind of the closer they are, right? If that overlap is less than 50% of the margin of error, right? That's when we start to say, yep, looks like these are probably statistically different at P less than 0.05. Again, this is kind of a rule of thumb, kind of like a quick hack on stuff, but this is oftentimes all we're left with if people don't give us the information that we need to have, right? So let's say someone gives us a confidence interval and a mean, but not a standard deviation. If I know my sample size, I could probably work backwards and get that, right? And this is the thing I do quite a bit, but this is nice knowing how this is all put together, because then you can reverse engineer stuff and get information that you want. Yeah.
So, just generally in the article, they say that the luck is about 0.5 or less than that.
Mm-hmm.
And you can say it's significant. Is that just because they're trying to stay away from this hard
Yeah, yeah. Hard rules of thumb are nonsense, right? Like, I don't know, give me something in life that's a hard rule of thumb all the time. I suppose I can give me some things. But in general, right, for the types of things that we do, right, this is where we get people like, oh, I heard this in my stat class one time, and this is the rule forever and for always. One, probably not. There are probably other sort of moderators, things that are coming in and impacting that. And then two, I don't know, maybe your person didn't know what they're talking about. So never trust anything I tell you. It's plausible, pending verification and stuff like that. So again, this is one of these things. It's a hard thing to get worked off of, or pushed yourself off of, like in undergrad, right? Like, oh, if this is less than 0.05, then it's significant. If it's greater than, it's not, right? And that's sort of the end of the story. In actual fact, we work in shades of gray and things that work on continuum, non-discrete categories. So wanting you all to think about, we'll talk about general rules of thumb as things start to approach this level. You might start to be concerned with different types of things, right? But, oh, you know, I met this threshold, and so that means X or Y. Hopefully in all aspects we start to push you off some of that stuff.
So say you got like a 0.6, how would you interpret that? Is it more open to interpretation?
A 0.6 what?
If your overlap is like 0.6.
Okay. I mean, probably I would say it doesn't, like, based on I would probably, you know, 0.5, 0.6, I would probably say there might not be nothing there, but based on these data, I don't have enough to say I don't have strong evidence to say these are reliably different. And then we'll talk about that today. A lot of our statistical tests, like, I don't know,
Okay.
it could be different, maybe it's not, I don't know, can't tell from these data. Yeah, Laura.
So in this example you have on the slides, you're comparing two groups, right?
Yeah.
On the graph that is on the board, there's 4. If you had 4 different conditions, would you compare the overlap of all the
You
combinations?
could if you wanted to, right?
Or, yeah.
It depends on your specific concerns, right? And we'll get into this when we get into some factorial stuff. You're going to be in a much better position if you have a handful of things that you're really interested in, as opposed to looking at all possible things with all possible comparisons. Then that's just a lot of information to deal with. Other questions? All right, cool. Some things to look at in terms of reporting confidence intervals. You can go through, take a look at that. But that picks us up today. So I'm going to switch on over and jump into distribution of sample means hypothesis testing. You know what? This is exciting. This is our 4th lecture. We're halfway through the class. We're basically finished up, essentially. We have 8 lectures. We're on number 4. I mean, we're making huge progress. We'll probably be done by Thanksgiving at this rate. But stuff we're going to work through today, distribution of sample mean, central limit theorem, get into the idea behind null hypothesis, significant testing, and then the heavy criticisms and all the flaws of our statistical procedures, right? My goal is you all become horribly jaded by the time we finish up. Just throw you all into existential crisis, right? Like, I don't even know what to believe when we get to the end of this. But if we're thinking about what we've done up to this point, and a lot of the stuff that you did in this, I've been working on in set 3. A lot of what you're doing is focusing on looking at the location of a point or a score in a distribution and calculating the probability of obtaining a score of this level or higher based on some population of scores or some sample of scores, right? But we're rarely interested in our applied research on one person's score and where that one person's score lands relative to other people's score. Now, clinical, this kind of comes up a little bit more. If I've got a client who comes in, I've got a nice validated measure, and we say, this is someone's score on a substance use measure or an eating measure or something like that. Maybe finding sort of their score and say that this person is at the 90th percentile of people within this. That is a useful thing, something we don't use enough. But in general, for research purposes, we're generally more interested in looking at and making inferences about some average score based on a sample that we've collected, right? But the nice thing is all the things we worked up to this point generalize nicely, sort of moving from individual scores within a sample or within a distribution of scores to looking at a mean within a distribution, within a larger distribution of means. So just like we've gone through determine representative probability of obtaining a specific value in a population or a distribution of scores, what we can do is we can take this and start using the same types of principles to look at how representative or how likely it is to draw a sample from a population having some specific aspects given the possibility of all of the possible means that could be drawn, okay? So, we're talking about distribution of sample means. Distribution of sample means is a distribution of means from all possible random samples of a given size that could be selected from a population, okay? So again, let's say that our interest is the height of undergraduates on University of Wyoming campus, right? That's a population, but it's a manageable population, right? And so let's say that we decided to go through and grab a sample of 100. So we randomly select 100 undergraduates from the University of Wyoming campus and measure their height, okay? The distribution of sample means would be all possible, the distribution of means of all possible samples of 100 that could be drawn from the population of University of Wyoming on-campus undergraduates, okay? So if we went through and actually calculated how many samples of 100 that could be drawn with replacement from all the undergraduates currently on campus, and then we went through and plotted out, ran a distribution of all those means, that would give us the distribution of sample means for that population, okay? And so before, what we were looking at distribution of individual scores. With the distribution of sample means, the values that we're working at are the means of a sample. So, in general, right, there's a countless number of samples that could be drawn for a given population, even if we're using a small population, like all undergraduates on the University of Wyoming campus. All possible samples with replacement that could be drawn from that sample of, how many undergrads we have here? Do you know, Angela?
It's like around 30, isn't it?
Oh, no, I don't think we're that big.
20 and then we're at 10.
Yeah, I think it's, let's call it 15. Let's say we got 15,000 kids on campus. All possible samples with replacement of 100 in a population of 15,000. That's an astronomical amount, right? There, we could never actually calculate that by hand. And so it's impossible to calculate and do this directly, but luckily we have math. We have mathematical theory, and we start to get some shortcuts, and we can start to see that as we start to do certain things, very quickly we can start to get a sense for what the population values are going to be. So for an example, let's take not a sample, or not a population of 15,000, let's take a population of 4 scores. Right? These 4 scores are all the scores in our population. These are the end all be all. It's just these 4. Okay, we've got a score of 2, 4, 6, and 8. They're nice even numbers, right? The mean of this population is 5. This is the population parameter. 5 is the population parameter. This is the true actual mean of this population of scores. Okay, but what's nice about this population of 4 scores is we could very quickly and easily, with only 4 scores, go through and graph out all possible samples of a given size based on these 4 scores. So let's say we want to construct samples with 4 scores in the population. If I'm pulling random samples of 2 with replacement, there's a total of 16 unique samples that I could draw with sample size 2. Okay, so my first sample, I pull a 2, put it back, pull another one, I get another 2. So this is my first sample. A 2 and a 4, a 2 and a 6, a 2 and an 8, a 4 and a 2, a 4 and a 4, right? So we're going through 16 with 4 scores. There's 16 possible unique samples of 2 that we could draw from this population, okay? So basically what we've done, we've recreated the distribution of sample means for this sample, or for this population of 4 scores, okay? People see what we've done here. Okay. If we then went through and calculated the mean of all possible samples of 2, this is what we would get. Okay? And so what we can then do, once we've calculated, once we've got all possible, this is physically, there are no more than 16. 16 is all you can get in terms of unique samples that could be drawn of 2 from this population of 4 scores. If we go down through and calculate the mean of each one of those samples and then graph those out, this is what we get. Yeah, Amanda, what happened to our distribution of sample means?
It turned into a normal distribution.
It turned into a nice normal distribution, okay? And this is what happens, right? Nick, what did our initial distribution look like?
Basically a flat line.
It's just a flat distribution, right? But when we go through and we calculate the sampling distribution of all possible means of n equal 2, all of a sudden we get a nice normal curve, right? Something that's nice and structured. And so what we find with sampling distributions, if we're talking about sampling distribution of the mean now, sampling distribution of other statistics starts to get a little bit different. But if we're talking about the sampling distribution of the mean, we find that the sample means pile up around the population mean. And mathematically what ends up happening is the mean of our sample means is going to be equal to the population mean. Okay? We also see that this distribution of sample means generally forms a nice normal distribution. And because of this, what we can do is we can start to answer questions. We can start to infer the likelihood of obtaining a given sample of a certain size, making setting probabilities of the probability of randomly selecting a mean of a given sort of score or above. Okay, so this is our original distribution, population mean of 5, right? We find that here the mean of our distribution of sample means, or the mean of all possible means of sample equal 2, is also equal to the population mean. Okay. So this is how we can start to say, if I get a sample of a certain size, and particularly if it's a large sample, from a mathematical standpoint, I can start to have confidence that the mean of my sample probably is pretty close to, or should be a reasonable representation of what the population mean should be, okay? And what we can do, in this simple block example, we can actually start to see where some of these probabilities are coming from. So, Evelyn answered, so what is the probability of randomly selecting a sample of 2 having a mean greater than 7 based on this distribution? 1 in 16, right? That one. There's 16 possible samples that could be drawn. One of them is greater than 7, okay? So is this a likely sample that we would draw, Emilio? No. Is it impossible? No. But it's unlikely, right? Now the trick is I don't know if this is the sample I've got. I don't know if this is on the end of the distribution or somewhere else, right? But in general, not knowing anything else, I would say it would be unlikely to draw a sample, randomly select a sample of this size based on my distribution of sample means. People sort of get a sense for what's going on with this. Okay. So, if we're not working with populations of 4, we're actually looking with real life populations, we're not able to go through and actually recreate our distribution of sample means. But we've got mathematical theory that helps us out with this. When we're working with actual statistics where these population parameters are theoretical numbers, right? They're not anything that I can actually ever measure, right? But this idea, in theory, there is an average score of all people in the world on something, right? And central limit theorem says that for any population with a mean of mu and a standard deviation of sigma, the distribution of sample means for sample size n will have a mean equal to mu and a standard deviation of sigma over the square root of n, and will approach a normal distribution as n approaches infinity. Okay? So what this is saying is that our samples that we collect, based on mathematical theory, assuming that we've got good representative samples, will start to follow certain types of rules that lend us to be able to make certain inferences about the relative population of interest. Okay? So, if we are looking at the distribution of sample means, some different characteristics that we can conclude with some certainty based on our central limit theorem. So let's say here that I have random samples of adult height of n equals 100, okay? And let's say that this is people in the US, okay? So my population are residents of the United States, okay? Now, I can't go through and measure all people living in the United States and get their average height. That's impossible. But if I'm selecting randomly selected people, a random sample of 100 people of everybody in the United States, and were to get their average height, and then do that again and again and again and again and again and again, what I would get would be a sampling distribution of means, right? And what we see is that this distribution of sample means approaches this nice normal curve if one or both of the two conditions follow. One, population from which the samples are drawn is normal, okay? Height, we're assuming that's probably going to be a relatively normal distribution, right? We're going to have some people who are very, very tall, some people who are very, very short, and some people, most people are going to fall right in the middle here, right? And so if the population that I'm drawing from on whatever characteristics that I'm measuring is normal, distribution of sample means is going to get normal very quickly, okay? Or if I have a sample, if I'm collecting sample sizes of 30 or more, even if I'm looking at something that's really skewed and ugly, right? Let's say, John, I'm looking at aggressive behavior in kids, right? That's something that's probably going to be skewed. Most kids probably aren't going to be aggressive. Some kids are going to be a little bit aggressive. Some kids are going to be super aggressive, right? Do you kid person or a emerging adult person with Cynthia?
I'm an emerging adult.
Emerging adult, never mind. With emerging adults, fine if you're going to screw up my example, right? I was trying to be nice, use something from your area. It's not, it's just, okay. But either we're looking at aggression, right? It's probably going to have a skewed distribution, right? But as long as I'm looking and sampling aggression from a sample that's 30-ish or larger, right? The distribution of sample means it's still going to turn out to be approach normality very quickly, okay? Think about this in our sample of 4 scores, right? That was a flat distribution. That wasn't even close to being normal, but our distribution of sample means did end up being normal, same type of thing. So if we're looking at it, thinking about distribution of sample means, distribution of sample means starts to become normal very quickly when one, the population, whatever we're measuring in the population, is expected to have a normal distribution, or we're collecting samples that are reasonably large, and reasonably large generally is sort of 30 or greater. Okay. Questions? All right. Central tendency, right? We find that the mean of distribution of sample means, the average of all possible means of samples of a given n is going to equal the population. Okay. So again, if I were to build a distribution of sample means of adult height in the of U.S. residents using samples of 100, the mean of that sampling distribution or the expected value of the mean is going to be equal to the true population mean here. We're saying the true population mean is 68 inches, right? That's what it is. If we took the mean of my sampling distribution, we call this the expected value of the mean of all possible means of a certain sample size, expected value of the mean is going to be equal to the population mean, okay? So we don't have to actually go out there and physically measure our population parameter. We can infer the population parameter based on this mathematical theory. So our expected value of the mean of a distribution of sample means equal to the population mean. People following me there? All right. And then if we're talking about variability, this is where we get in our standard error. Standard error in this whole sort of idea of sampling distributions is just a fundamental, lies at the very core of any type of analyses that we're going to be doing. So I really want you all to have a strong understanding of conceptually what this is. So we've talked about the shape of the distribution. We've talked about the measure of central tendency of the mean, expected value of the mean. Our measure of variability for our sampling distribution is going to be our standard error of the means, or our standard error. Standard error is going to be our standard deviation divided by the square root of n. This is essentially the standard deviation. Your standard error is your standard deviation of the distribution of sample means. Okay. Your standard error is going to tell you a number of different ways we can think about standard error. We can think about standard error as an index of how much different one expected sample is going to be falling from the next, right? So just like we talked about standard deviation before, standard deviation in a sample of scores, right? We say our standard deviation is the expected, sort of roughly speaking, the expected value or the expected difference of any randomly selected score from the mean, or the expected value of two randomly sampled scores from one another on average, right? Same thing applies when we're talking about standard error. If we're interpreting standard error as how much different expected from one sample to the next, let's say Layla's looking at levels of depression in people who've been exposed to natural disaster, right? And you've got a nice sample of 40, right? You go through and you get a mean value of 52, right? And then you go through and you find that your standard error for that is 6, right? Your standard error is telling you, if I were to go through and grab a new sample of, what did I say, 40? A new sample of 40 scores, how far would I expect that separate sample on average to deviate from my first sample? My standard error is 6, or then I'm expecting about a 6-point difference, right? As my sample size starts to increase, instead of a sample of 40, I got a sample of 100. What's that gonna do to my standard error?
It's gonna decrease.
I'm gonna make it smaller, right? I've got a larger sample. I'm expecting this to be a much more stable estimate of the population mean, and so I'm going to expect that score on replication to jump around quite a bit less, right? So we can think about a standard error as how much different to expect from one sample to the next. We can think about the standard error as a measure of how well any individual sample mean is an estimator of the population mean, how much error we have, right? So here, with sample size 100, if I have my standard deviation is 6 inches in the population, with a standard deviation of 6 divided by square root of 100, that gives me a standard error of about a ½ an inch. How good of an estimator, Evelina, is my sample mean with standard error of 0.6 if I'm talking about adult height? If my standard error is ½ an inch.
So the standard error is the mean of your sample is ½ an inch.
No. The mean of my sample is whatever the mean of my sample is, right? But my standard error is a little over a ½ an inch, right? Given what we know about people's height, is that a pretty precise estimate? Yeah.
I don't know why.
Yeah. Okay. So someone help. So why is this? Why would we say? Why would I be very happy if this was my standard error? What do you think, Emilio?
Well, because people's height varies by, half a foot, inches, so a ½ an inch variation is not much at all.
Right.
Compared to the
So
scale.
basically what I'm saying is that if my standard error is a ½ an inch, and my task is to get a good bead on the average height of adults in the U.S., right? And I calculate my standard error to be a little over ½ an inch. I'm pretty excited about that, right? That means if I were to grab another random sample of adults and measure their height, or another random sample of 100, I'm expecting whatever I get from that sample to, on average, deviate from my first sample about a ½ inch, right? I mean, it might be more, it could be 3 inches, right? But if I keep doing this over and over and over again, I'm gonna expect on average differences across my samples to be about a ½ inch. And then practically, if I think about what I'm measuring, ½ inches, I mean, we fudge ½ inches all the time. Oh, I'm 5'2½". Like, okay, well, whatever, right? It's not that much. It's pretty precise given what we're looking at, right? So we can think about our standard error is telling us how much, how good our estimate is, or how close our estimate, or how adequate our estimate is of population mean, telling us how much error. Or we can think about this as the expected difference between any randomly selected sample and the population mean. Same type of thing, right? If my standard error is a little over ½ an inch, that's saying that any randomly selected sample of sample size of 100 is expected to deviate from the actual population mean by about a ½ inch. I'm pretty happy with that. That's pretty precise, right? So even though, in general, right, the random, let's say, and I don't think I just kind of made this up, but let's say on average, if we're combining men and women, on average, any two randomly selected people from the population of residents of the U.S. are going to differ about 6 inches in terms of their height. That's a pretty big difference, right? But if we're thinking about our average score, average height is only going to, any randomly selected sample of 100, our mean height for that sample, we're expecting that to only deviate from the population, the actual population mean, on average by about a ½ an inch, right? Now this doesn't say we can't end up way out in a tail, right? I go through and I calculate get a randomly selected sample, and it says average sample of people in the U.S. is 5'4". Given what I know, I should probably expect that to be not a great sample, but sometimes we're going to get out here, sometimes we're going to be way out here, but on average, right, we're going to be right there in the center. Okay. Questions about standard error. Think about standard error as the standard deviation of your distribution of sample means, okay? Or your distribution of any type of sample statistic. If you have a good understanding of standard deviation and how to interpret standard deviation, this will be a nice way to think about conceptually what a standard error is and how and sort of how you would put a practical interpretation on that. Questions on this? Angelina, is standard error important?
So I have a question.
Yeah.
If you were doing your own research, or if you were looking at research samples, and let's say there were 5 replications of a sampling, and the standard error was all over the place between the 5, what would that mean? That you have 5 bad samples, that you have, I mean, like, I don't, what if what you're getting is super inconsistent across the board? Well,
and this is what happens with replication on our studies, right? It gets a little, this is a very straightforward situation, but as we start to add additional things in there, it starts to get tricky, right? Because maybe my first sample was drawn from, so I do trauma research, right? So maybe my first sample was drawn from trauma survivors in one part of the country, like domestic assault survivors in one part of the country, but my next one was drawn from a different part of the country. I don't know, maybe the systematic is maybe not the same. I mean, they're not the same population, right? So we can have differences there. We can have differences in terms of the methodology, right? So these were the procedures we used in this study that differed in maybe a small way or a large way for another study, right? And that's going to make things different, right? And so if someone is done, right, again, if we're randomly selecting, right, because I could get my hands on a list of all on-campus students at the University of Wyoming. If I randomly selected with replacement 100 students to go through and measure their height, and I just did that again and again, grabbing people from Prexis and getting their height, that's not a random sample. I'm not using, that's not a random sample with replacement. People are going to say yes, people are going to say no. I can start getting, maybe tall people are more confident and say yeah, sure, and short people like, leave me alone, I don't want to tell you how tall I am type of stuff, right? These are the types of things that can go through and start factoring into some of this stuff. But in sort of a perfect world within the context of mathematical theory, this is how this works out.
Okay.
But if you do start to see things jumping around, you might say, well, is this just random stuff, or are people systematically doing different things across sites over applications? Other questions? All right. Factors impacting our standard error. Standard error decreases with population standard deviation. Okay. Remember that my basic formula for standard error is my standard deviation over the square root of my sample size, right? So if this gets smaller, what happens to my standard error? Standard error gets smaller, right? If my standard deviation is a smaller number, it shrinks down my standard error because there's less stuff going on, right? But we don't have control of our population standard deviation, right? Population standard deviation is what it is. And so other thing that goes into this is your sample size. And the law of large numbers says the larger the sample, the more likely it is that the sample mean will be close to the population mean, right? If I go through and grab 4 people walking through Prexis and turn them, so use that as my indicator of average height of University of Wyoming undergraduates, that's probably not going to be great, right? If I get a random sample of 150, that's going to be a much better estimate, right? I'm going to get people at the extremes. I'm going to have a better chance of capturing some of the variability. So as my sample size goes up, I'm expecting my estimate of my parameters to get much, much better, much more stable. And so as my sample size goes up, Laura, what happens to my standard error?
As the sample size goes up?
Yep.
It decreases.
It decreases, right? And this is what we can use to drive our standard error. So spoiler alert, your standard error is what goes in the denominator of your test statistics, right? Particularly your means-based stuff. So Nick, what happens is to my test statistic is my standard error shrinks. It gets bigger, right? If we're talking about t-tests, we want bigger is better, right? Because that tells us sort of we have more power. So if we're looking at, if I were to go through and graph, which I did, you can thank me later, looking at, for a given standard deviation, as our sample increases, this is what happens to your standard error. So it's not a linear function, right? But if I plot out in Excel, if I have a standard error or a standard deviation of, say, 5, and then I start dividing that by the square root of, it looks like it, 1, I must add standard. So this is a standard deviation of 15, right? If I start calculating and plotting standard error as sample size starts to increase, this is what we see, right? So we see standard error shrinks very rapidly until we get to here-ish, right? And then the addition of additional people starts to sort of decrease sort of more and more, right? So if I add 20 people to my sample of 10, I get a huge reduction in my standard error. If I add 20 people to my sample of 150, the benefit to my standard error is much more modest. It's still good, right? But it's shrinking it by a less amount. So when we're talking about, when you hear this rule of thumb, a large sample is 30. That's what this is referring to, because about right here, diminishing returns for adding, or so your additional returns on adding larger, more people to your sample in terms of your standard error starts to become considerably less than it is in these samples. Okay, so in general, rule of thumb, in terms of if we're thinking about the distribution of sample means, sample size of 30 is large. Can you run around and start declaring sample sizes of 30 is large for all analyses ever and for always? Don't do that. People will do that. 30 is not a large sample. 30 is a very small sample, particularly for a lot of the regression types of analyses we do. But if I'm running sort of an experimental design and I got 30 people in each one of my cells, is that pretty good? Yeah, that's A-okay, right? So thinking about just understanding where this kind of rule of thumb comes from for a sample size of 30 is large. Within this context, yeah, because the addition, the improvement you get on your standard error after that starts to decrease. It'll continue to go down, right? It's just getting less and less relative to what happens on the front end. Okay. Questions about this? Cool. All right. So if we're going to look at our distribution of sample means, so distribution of sample means for IQ, so a mean of 100, and so here we have the distribution of sample means for IQ for samples of, let's say, 5, 20, 50, and 100, okay? You can start to see that for the distribution of sample means, right? The mean, right, the expected value of the mean of your distribution of sample means is identical whether or not we're talking about samples of 5, 20, 50, or 100, right? So the mean of the distribution of sample means, your expected value of the mean stays the same. What's changing here, Katie?
Sorry, do you repeat that?
Yeah, so the mean of each one of these distribution of sample means is staying the same, right? So the expected value of the means, what's differing as we go from samples of 5 to 20 to 50 to 100? The variation, right? And what do we call the variation of distribution of sample means?
The word.
Your standard error, right? Your standard error is getting smaller and smaller as your sample size gets larger, right? Yeah. When in doubt, just guess standard error. Statistically, it's a good guess. So what we're seeing is as our sample gets bigger, right, our variation around that true population parameter gets smaller and smaller, right? With a sample of 5, our expected value or our individual means of sample size 5 is going to jump around a whole lot, right? But as our sample starts to get larger and larger, the mean of those samples is going to get tighter and tighter around this true population parameter. Questions? People getting a handle on this? All right. So working with up to this point, just try and sort of organize this in your head. We talked about 3 different types of distributions up to this point in the class. We've got a distribution of our population scores, right? This is going to contain all possible scores in a population, going to have its own mean, shape, and measure of variability, okay? So if we think about this is a population of height of residents of the U.S., that's all possible, or all people living in the United States. That population of heights can have a shape, mean, and measure of variability. We also talk about distribution of sample scores, right? So I go through and I'm going to collect a sample of 100, right? Randomly, I somehow get a random sample of people. Maybe I look at census data or something like that, right? It's about as close as a true sample, and I randomly select 100 census responders and record their height. That's going to be a subset of scores from the larger population that I hope is representative, and it's going to have its own shape, mean, and variability. Then I'm going to have the distribution of sample means. Distribution of sample means is the sample means from all possible samples of a specific size that could be drawn from a population, and it's going to have its own shape, mean, and variability. Okay. So if I'm looking at, so here's IQ scores, right? Here's my population distribution, right? Mean 100, standard deviation of 15. But I go through and I sample 30 people. My sample of 30 people is going to have a mean of 102 and a standard deviation of 15.6. Okay? Haley, what do I call the difference between this number and that number?
That's the parameter and that's the statistic.
Yeah. What's the difference between those two numbers?
Standard error.
Not quite. But that's a good guess. So what's the difference between my population parameter, my sample statistic. Sampling error, fantastic, right? It looks like this sample was a pretty good sample of this, right? We're off by 2 points, right? Angeline is 2 points on an IQ cognitive achievement test, pretty close, right? We've done a nice job. We're about 0.6 of a unit off in terms of my standard deviation. We're doing pretty good. We've done a nice job with this, right? But do we have a nice normal distribution with this sample of 30? No. I mean, it's not pretty, but it's about what I would expect from a sample of 30, right? It's not terrible, but it doesn't have this nice curve, right? But if I were to go through and calculate distribution of sample means for sample size 30, right? If I went through, if this is people in the US, and I went through and got sampled with replacement, samples of all possible samples of 30 that could be drawn from the population, and then graph those, the average score from that sample, I would have my distribution of sample means. And here the mean is 100, identical to this, and I've got a sampling, a standard error of 2.8, right? This is my standard deviation for my distribution of sample means. Based on this calculation, I would expect that any two means or the average IQ score from any two samples of 30 would jump from be about 3 points different from one another, or any randomly selected sample of 30 from this distribution to be on average about 3 points from the actual population. That doesn't mean everyone is going to be, right? Because we get things hanging out there in the end, but on average, we would expect about a difference of about 2.8 points. Okay. Yeah.
I don't know if this matters, but when you're having the distribution of siblings, are you always talking about sampling with replacement from the population?
Mathematically, we're always talking about sampling with replacement. Now, we obviously don't do this, right? Because we don't, in our studies, we don't sort of have the same person participate 7 times, right? That'd be nice, but this violates some assumptions. But from a theory-based standpoint, yeah, it's always with replacement. Good question. Other questions about this stuff? Okay. Now, I'm glad you're all sitting down. Just hold on to your socks, because what I've done, I've got a screencast video going through, like, demonstrating distribution of sample means, right? So the actual data in SPSS generating a distribution of scores, and then going through and pulling random samples from that and plotting those out and showing how all this stuff works. Maybe if you're not doing anything this weekend or want to just hang out, about a 30-minute stat video, it's exciting stuff. But again, this is such a foundational and important piece of understanding sort of why our statistics work the way they do. We'd strongly recommend going down through and sitting on that. It's just going to help solidify this. You actually see sort of, how I can kind of see how that actually works in practice. I mean, it's not just like in theory this should happen. Well, I mean, it is that way. But when you actually go through and run these numbers, it actually turns out really, really nice the way it should. So I'll go through and make sure you all have a link to that, and that's posted. But again, if any of this is feeling a little bit fuzzy, would recommend go through and taking a look at that just as a sort of way to get strong on this stuff. Okay. You guys can get together, right? Like to get a pizza, some beers, right? So like the cast it on the big screen, something like that. Okay. Let's go through, take a break. Come back in 10. Questions on anything that we've worked through up to this point?
You said that the video will help solidify.
Yeah. So it'll go through. And again, I suspect this probably isn't the first time that you've been introduced to this stuff, but I think it was maybe one chapter in an intro stat class that we just sort of moved through quickly, and then didn't worry about, because we're more worried about you being able to tell whether or not some value is greater or less than p equal 0.05. So, but this is gonna be an important thing to go through and know as you start to get into more complex statistical analyses and when we have violations. I mean, this is essentially a basic violation. So when we have violations of our statistical tests, right? Our statistical tests are assuming something like this where we have known properties of a distribution. Well, we have known properties of a distribution under these set of assumptions, and when we violate those assumptions, then we start to not know exactly what the specific characteristics of these distributions are. And if we don't know what the specific characteristics of these distributions are, we have a hard time assigning probability values to obtaining a score of at this level or higher, which starts to then throw off all our inferences, right? And so, again, this is going to be really important for understanding standard error, what it is, how all these statistical processes start to go in. So, again, that video should provide you some additional examples and things like that. But if you have questions, come talk with me and we'll get things squared up. So, why is this all important? Again, if we know distribution, what the distribution of sample means should look like, what we can start doing is finding the probability of randomly selecting a sample that has certain types of characteristics, right? Basically, we can say, what's the probability of randomly selecting a sample having mean M or greater, right? Or less if you want to do that, right? And so this already gets into some of our very most basic tests, our z-test. Z-test for sample means what we can do is we can start locating specific probabilities by calculating a z-score based on some our distribution of sample means, and we can start to locate probabilities associated with the random selection of specific samples. So our z-test is going to be mean minus our population value over standard deviation of the mean here, or basically our standard error. Okay, so for example, if we say SAT scores form a normal distribution, mean of 500, standard deviation of 100, what's the probability of randomly selecting a random sample of 10 students with a mean SAT of 440 or less? Okay, so average is 500. How likely is it that I'm going to just go through and randomly select 40 students and end up with a mean of those 10 students having a mean SAT less than 440, right? We can say, what's the likelihood of selecting a random sample of 75 students with a mean SAT less than 440, right? Nick, any thoughts on which one of these is less likely?
Probably the 10 students.
Yeah, why is that? You're absolutely right.
Because you're probably going to have more variability when you have the 75, you're more likely to be closer to that mean.
Yeah, I would give you a high five. That wouldn't inflect you with some sort of plague, but you're absolutely right. If I have a sample of 10, right, that's going to jump out. That could jump around a whole lot, right? But if I have a sample of 75, this is a long ways off of. This is quite a ways underneath my mean, right, or my population mean. Assuming that this is a representative sample, it's probably going to be quite unlikely that I would get a sample that low. I could also say, what's the range of mean values for sample of 25 expected to form the middle of 80% of the distribution of SAT means, right? So again, some of the same questions that you're working at in this set, we can do the same thing if we're thinking about the likelihood of getting samples of a certain characteristic as opposed to single scores out of a distribution, but the basic idea still holds. Okay. So when we're taking a look and we're interpreting our patterns of data, a couple different possibilities. One, we have some systematic factor that is representing some real association, right? I'm seeing a difference in samples drawn from these two different populations because these two different populations are different on whatever it is that I'm looking at. There's an actual difference there. Or it's just random fluctuations, right? It's just chance fluctuations. I say I have population 1, population 2, right? Population 1 has the exact same mean and standard deviation as population 2, right? And I go through and I pull a sample from population 1, pull a sample from population 2. Amanda, are my samples going to have identical means?
Most likely.
Are they going to have identical standard deviations? Probably not, right? These are gonna vary a little bit, right? So even if mean and standard deviation for these populations are identical, I'm probably gonna get some difference between my two means. My question is whether or not this is something that's actual, the difference that I'm seeing in my two sample means, is that something that reflects a difference, true difference in the populations, or is this just random error, right? Because they're never gonna be identical, right? And this is where null hypothesis testing comes into play. This is what we're using to try and add some structure to how we start generating inferences about whether or not differences in patterns of data are representative of true difference in populations, or if these are just random effects that are floating around due to sampling error and things along these lines. Okay. So if we're on a hypothesis test, what we're doing is we're trying to use our samples to make some inference about a population, some unknown population value. We can't directly observe the population, but we can get pieces of it, right? And hopefully we're getting representative pieces of it, right? And so our questions are, if we assume that a population has some mean value mu, what's the probability of drawing a sample from that population with a mean at or more extreme than some sample value that we've got, right? So if I say that my population has a mean of 100, right? This is my assumption. I'm assuming that the population has a mean of 100. How likely is it that I would randomly draw a sample that gives me an average score of 110 or above, right? Is this something that's likely or is it not likely, okay? If we determine the probability that it'll be low, right, it would be uncommon to randomly draw a sample with these characteristics. We would typically, and we'll talk about why this is problematic, but a general convention is to conclude that the population from which the sample was actually drawn has a mean that's different from our assumed model, right? So I go through, say, my model says the population value is 100, and I pull a random sample of 100, and I find that the mean for my sample isn't 100, it's 115, okay? Is this likely? If it's not, what I'm saying, or what I'm inferring is that, well, it's probably likely that the actual sample, the actual population mean of this, the actual mean of the population from which this sample is drawn isn't 100, it's some other value. My best guess is 115, right? But if based on my statistics I find that it's not terribly unlikely for me to get a sample with a mean of 115, then I say, well, seems like 100 could maybe be a reasonable estimate for the population value from which this sample was drawn, okay? So to put kind of a more concrete example, let's say that I know I'm a rat researcher. Anybody done rat research or animal research? Okay, let's say that I've got a sort of genetically identical, these white rats, and they all sort of have basically the same properties for the most part, right? And we're saying that the known population of these rats is 400 grams, right? That's what the population of these rats would weigh, right? And so I go down through and I pull a sample of these rats. Then I give them some sort of treatment. I pump them up with steroids, or I sort of restrict their diet in some way or something like that. Now all of a sudden, my sample is a treated sample. It represents a different population. The population that these rats represent is some hypothetical population of all possible rats that could sort of have this treatment. And so what I want to know is the population of my medicated rats equal or different than the population of known rats here, right? So what we've done is we've drawn a sample, done something to them, and by doing something to them, we've now made them a population. This is a different population, or these are members of a different population than that. That's everybody where we don't screw around with them. This is rats that we're screwing around with. I don't know what the mean weight of screwed around with rats is. What I want to know is if it's different than this population estimate of 400. Okay, and so if the average weight of my sample rats here is much larger than 400, then I'm going to infer that probably what's happening is this hypothetical population has some different population parameter that's different than 400, either larger or smaller from this. Okay, so again, remember that we're never interested in the sample. The sample is just our mechanism for getting at these population values. Questions about this? Okay. So, let's say that we believe antioxidant supplements might reverse age-related cognitive decline. So you sample 25 adults age 65 or over, and we give them antioxidant supplements for 6 months. Participants are getting given a neurological test to assess cognitive functioning. Scores for this test are known to be normal in the population, with adults 65 and over scoring a mean of 80 and a standard deviation of 20. Okay. So in this situation, we have a test that's been standardized. We know what the population value is on these tests, on this test for the general population of older adults 65 and over. Our question is if we have someone, or if we have older adults on antioxidant supplements, we've got a new population, right? Amelia, what's my new population?
It's gonna be the one with the antioxidants.
What's that?
The population you're testing is the one with the antioxidants.
Yeah, right. So we've got a new population, right? This is the population of older adults who use antioxidants, right? Because we've created them, we've made them, right? They represent a new population. Now that new population might have different cognitive functioning than the original population, or it might just have the same population values. What we want to do with our statistical analyses and our hypothesis test is try and tease that apart, okay? So what we're going to do is we're going to state our hypotheses, right? These are predicting our characteristics of this to be collected sample. We haven't collected the sample yet. We're saying these are what we're expecting to happen in this sample that we have yet to collect, okay? We're going to set a probability criteria for determining what we're going to call a reliable effect. We're going to collect our sample, compute relevant statistics, confidence intervals, effect sizes, things along those lines, and then we're going to draw conclusions about behavior of the population based on these data, okay? So this whole thing that we're doing here, our intent is to try and learn something about the characteristics of older adults who use antioxidants. That's our population, right? And so what we're going to do with this experimental test is we're going to create a sample from that population by getting a sample of 25 older adults and then having them take antioxidant supplements for 6 months, okay? And then what we're going to do is we're going to say, based on the scores we get in that sample, can we make an inference that mean cognitive functioning in the population of older adults who take antioxidants, is it different than just the general population of older adults? Questions about this procedure here? All right, step one. First thing we're going to do is state our hypotheses. As you're probably aware, we actually have a couple of different hypotheses. Our null hypotheses, statement that there's no relation between the IV and the DV in the population, okay? Antioxidant, essentially what we're saying is that antioxidant use is unrelated to cognitive functioning. It's 0, right? Treatment has no reliable effect on outcome. This is our null hypothesis is saying that there's nothing happening, nothing going on here, right? Our new population is going to have the same parameters as some known population of individuals. Our alternate hypothesis is going to say a relation exists between the independent variable and the dependent variable in the population. We're saying functionally that our treatment has some reliable effect on our outcome here. Okay. Now our hypothesis test only tests the null hypothesis, okay? And based on the evidence we get from our sample, we either reject the null or we fail to reject the null, okay? Our null hypothesis is the only hypothesis that's of direct concern. We're not testing the alternative hypotheses here, okay? Other thing to remember is our hypotheses are always about our population, right? Someone will do this because it always happens. Someone will say the mean of the sample will be X. Absolutely not. I don't need a statistical test to tell me whether or not the mean of my sample is 80. Why? Because I just calculate the mean of my sample. If that number is 80, then I say, yep, it is. And if it's not, then I say, nope, it's not, right? I don't care what this sample mean is. What I want to know is whether or not I can infer from this sample, is this my sample mean far enough away from my expected value under the null hypothesis so that I can say, yes, this sample probably represents a different population or represents a population with different parameters than my what are assumed under my null. Okay, So I'm only testing the null. So hypotheses are always about populations, not about samples, right? And as I'm going through and you guys are working through and writing statements of your null hypotheses, make sure you're specifying the population, right? So, and don't say there's no effect, because that's going to be wrong. I want you to tell me what the population is, what effect we're talking about. I want you to be thinking about this. We don't do this enough, right? We just do research with undergrads and then say, yeah, I've got effects, right? When really, if we're sampling from our undergrad participant pool here, who's our population? What do you think, Elena?
All undergrads?
What's up?
All undergrads? Like,
Not really.
all people?
What's up? That might be who I would like to generalize to, but technically, who am I sampling from? What population am I sampling from?
If you're just looking at undergrads?
Here at the University of Wyoming. It's akin to we end up with a convenient sample from undergraduates taking intro psychology courses at the University of Wyoming, right? Now, whether or not that population actually generalizes to other people, that's a big question, right? Haley, you're doing jury research, right? And so you get responses from undergraduates, 18 to 20-year-olds, recruited from undergraduate classes at the University of Wyoming, right? And you find some effects, right? The extent to which that generalizes to actual juror members out in the population, that starts to become kind of a questionable thing, right? We would like to, and we conveniently ignore what population we actually pulled from, right? And we're saying, oh yeah, well, it's probably good enough, right? But that starts to become very questionable. The population we pulled from is a very different population than the population we're trying to make inferences on, right? And so then we get kind of there's some problems there, right? But if Kate's doing stuff on, Kate, what's your substance of choice, Kate?
Alcohol.
Okay. Kate's wanting to do alcohol research. Is the population of undergraduates at the University of Wyoming representative of undergraduates in general? Probably an easier case to be made for that, right? Now there's going to be some cultural differences, things along those lines that we might have to consider, but that's a little bit easier, right? Now let's say I'm doing reaction time and attention stuff, right? Something that's very sort of basic and hardwired biological in nature. Well, then it's probably, I mean, unless we're getting differences in age and things like that, then that's probably, my general feelings about rodeos in the Republican Party is probably not having a big impact on sort of how my brain is processing basic information, right? But if I'm looking at something that has to do with how my perceptions of the legal system and sort of things along those lines, then that starts to become problematic, okay? So this is my extended tirade on why you need to be thinking about what population have I drawn this sample from, and what types of things do I now need to starting to think about in terms of, I've made some inferences about a population, what population am I actually making inferences about? So I'm gonna twist your arm and make you tell me what populations we're making inferences about as you're working through these statement of your hypotheses, okay? So again, null hypotheses, only the direct is all we're concerned about here. So in our supplement example, here we're going to say in statistical notation we're going to have U of supplement equals 80. We're going to say the average cognitive function you score in the population of older adults using herbal supplements is equal to 80. Okay. So see here, I told you what parameter I'm looking at. We're talking about cognitive functioning. I've identified, sort of made sure that you know that this is referencing older adults, all the relevant information so that I know what you're talking about, and also helping cue you in and keep you cued in on what you're talking about too in terms of sort of the sample and the measures that you're collecting. Our alternative hypotheses is mean supplement or the cognitive functioning score in population using supplements not equal to 80. Average cognitive functioning in the population of older individuals taking herbal supplements not equal to 80. Okay, you don't have a directional test here. We could be greater, higher, or lower, but this is a general setup of how we would set up a statement of null and alternative hypotheses here. Questions with this? Okay, so got our hypotheses. Step 2, set our decision criteria. What we want to do is we're saying want to set the probability of obtaining the sample data, assuming that our null hypothesis is true. This is how we're going to start to make inferences about whether or not the population of older adults using herbal supplements actually likely has a cognitive score that's different than 80. Okay, if we find our sample mean to be much different than what we expect within the context of our model, right? Our null hypotheses. We can interpret these data as incompatible with either our null hypotheses or the assumptions of my underlying statistical model, and this starts to become important, right? So I'm saying that in my statistical model, I'm saying the expected value is 80, right? Now, if I get a value, a cognitive functioning score that's very different than 80, that could mean either, well, that these data are incompatible with my null hypotheses, that the average cognitive functioning score in the population of older adults taking herbal supplements is probably something that's different than 80, right? Or it could mean that the data that I've collected aren't consistent with the underlying assumptions of my statistical model, and this is important, right? Because I can go through and I have assumptions of my model X, Y, Z, and Q, and then I go collect data that are way off base, way over here, right? And I find a significant effect. Well, I don't know if that's because I have evidence against that doesn't support my null hypotheses, or if I've just done something crazy, right? I mean, I can say my null hypothesis is that foreign cars are the worst, right? Foreign cars run terrible. But then if I get my foreign car and I fill it with diesel and don't change the oil and run it into telephone poles and it all falls apart, I can say, well, either this didn't run well or I didn't adhere to the standards of driving the car, right? I don't know which one it is. Well, in that case, I probably do, right? But this is why it's important to go through, test your statistical assumptions, because you want to know that you're at least playing by the rules. Because if you aren't, and if you're ignoring outliers and distributional weirdness and other types of things, and you find a significant effect, I don't know if it's because I have evidence against my null hypotheses or just because I've got weird data that don't adhere to anything that I'm supposed to be doing with stuff. So something to keep in mind, because our null hypothesis doesn't tell us which one of these things are problematic, right? But what we can do is we can go in, start checking out our statistical assumptions to make sure that if we do find evidence that suggests that these data are unlikely, assuming the null hypotheses, we can rule out the possibility of B, right? And this is why we're going to go through, spend a lot of time working on assumptions, making sure that our data are within bounds of what's reasonable given our statistical test. Okay. Questions on this? All right. Sample means similar to the hypothesized means are interpreted as compatible with our null hypotheses, right? If I say my expected value, a cognitive score in older adults using antioxidant supplements, say the population of just older adults in general is 80, and my sample of older adults using antioxidants is 83, I'm probably going to say that, well, that's reasonably compatible with what was expected under the null hypotheses. And so our null hypothesis here is telling us whether our data is unusual, assuming our null hypotheses, but again, doesn't say that any model, that the model itself or any aspect of the model is necessarily correct. This is a methodological issue, right? So, Emilio, what are your interests?
Aggression.
Okay, so Emilio is interested in aggression, and his model says that space aliens come through and implant aggressive impulses in people, and that's why people act aggressively, right? And so he runs an experiment where he has people come in and he shows them images of space aliens shooting people with lasers and them exploding, and finds that people, after having watching this prime, are now more aggressive. And so Emilio says, sweet, this is evidence for my model, right? Well, he has evidence that showing people getting shot and exploded by space aliens has an impact on some aspect of their aggressive responding. That doesn't say anything about his model, whether his model is correct, whether any of his assumptions are correct. It just says that it looks like if we do this, we do see a shift in aggressive responding, right? This is another thing that we are really, really bad about, right? We have a model, or we have a research question, and we find some sort of significant effect and then claim evidence for our underlying model, which is fine as long as we recognize that the statistical test in and of itself doesn't prove anything about our model, right? We can say whether or not these data are consistent with expectations under our model, but it's not proof of our model, because our proof of our model can be, because our model could be consistent with a lot of different things, right? There are a lot of things going on in this study that could cause increased aggression that have nothing to do with space aliens, even though space aliens are part of the prime that you use, right? Space aliens, more likely than not, have nothing to do with any of it, right? And we'll talk about this a little bit more when we start talking about limitations of our null hypothesis testing stuff, okay? So, when we're setting our decision criterion, right? So we need to go through and we need to say, all right, this is what I'm willing to say is consistent with the null hypotheses within my model. Anything outside of this, I'm going to say is incompatible. And this threshold is determined by your by the investigator, kind of, right? This is related to our alpha level. This is our alpha level is used to define our critical regions. These are our benchmarks for determining whether or not something is implausible, assuming that the null hypothesis is true. Okay. Now, in actual fact, we don't get to set this, right? I can't run a project and just set my alpha at 0.25 because no one's going to accept that. We're going to say that's too much, right? Within psychology, our general convention is saying anything at alpha 0.05, right? So 2.5% in each tail for a two-tailed test is where our benchmarks are. We can make that more stringent if we would like, but if you're going to make that less stringent, you're going to have a good justification for setting your alpha level any lower than what the conventional standards are. But technically, your decision criteria are determined by you. It's just whether or not you can get anybody to publish it if people are thinking you're being too lenient with stuff. Okay. Questions on this? All right. So this is going to be our distribution of sample means, assuming that the null hypothesis is true. Okay. High probability values here in the middle. We're going to set our alpha equal to 0.05, and so this is going to be our critical region, right? If we go through for this z-test, and we go through and we set for a two-tailed test with alpha equal to 0.05, what are the z values that are going to define my critical region here? What do you think, John?
What the z-score would be?
Yeah.
I guess whatever would include like the R would be 1.96.
Perfect. There we go. Plus or minus 1.96, right? So we're seeing that antioxidants are our null hypothesis that antioxidants the average cognitive functioning in the population of individuals taking antioxidant supplements is going to be 80, right? And so this is, so under the null hypotheses, we're expecting this to be 80, right? And if we calculate our z-scores, we've got negative 1.96, positive 1.96. And so if we find a test statistic that falls within our expected region, we're good to go, right? Or we're not, well, no, we're not good to go. It's just saying that the data that we've collected are consistent with our assumption that the average cognitive functioning score in older adults taking antioxidants is 80, right? So it might not be exactly 80, but these data aren't inconsistent with a population estimate of 80 in terms of our scores. But if we get something down out here in our critical regions, this is where it's starting to say that, yeah, these data are unlikely, assuming that the null hypothesis is true, and this is where we would reject our null hypotheses. In here, we fail to reject. Out here, we would reject the null. Questions on this? Yeah.
Is it 1.96 because that corresponds to a confidence interval values?
We're all working with, so your confidence interval and your statistical test, all working with the same piece of information, okay? It's sort of like a recipe, all the same ingredients, just this looks a little bit different than that, depending on how we present it. Now, confidence intervals, interval estimates are actually more informative, give us more information than our statistical tests do. But there's nothing that we get from our statistical tests that we can't get out of our confidence interval except for a specific p-value. And as we'll talk about, specific p-values are kind of limited in their use of much in terms of interpretation. So we'll talk about how to integrate your statistical test and confidence intervals for this type of test, for a z-test, right? Our 1.96 is our 95% confidence interval. And so again, we're saying 2.5, 2.5 here. Same thing with our test. This is going to be what we refer to as our critical value. Critical value here is going to be z equals plus or minus 1.96. So it's still coming from the z table, just like as we had used before. Absolutely right. Other questions? All right. So step 3 is going to be a calculation of our test statistics. In this very sort of basic scenario where we're comparing our sample values against some known population parameter, what we're going to do is we're going to calculate our sample statistics and compare these using a confidence interval and then also a test statistic. Confidence interval, we've calculated these already. This is just going to be your point estimate corrected from your sample plus or minus your critical value for your z distribution multiplied by your standard error. Okay. If we're using our test statistic with a one sample z test, as in this example here, we're going to calculate a z score calculated to locate the position of our sample mean relative to assumed distribution of sample means under the null hypothesis. So I'm going to say pull this back. This is the mean of cognitive functioning scores in the population, right? What did I say? 8? Did I say? What was my standard deviation? 8. No, that my mean. What was the standard deviation doing? 15, 10. 20. Okay. So, this is my distribution of scores within the population, right? And so what I'm going to do is I'm essentially going to go through and I'm going to say, if my population or if my sample is actually drawn from a population with a mean of 80, right? What's the reasonable range of scores that I would expect? Assuming a mean of 80 in my population that I would expect of a randomly selected sample of, how many people did I have in my sample? 15? Do you remember?
25.
25. Okay. Okay. So what I'm going to do is I'm going to say, okay, I'm going to calculate a test statistic, and I'm going to say, here's my sample mean. I'm gonna subtract that from my population mean, my population mean under the null, okay? So I'm gonna get essentially a deviation score up here. How much of a difference is my sample from the expected value under the null hypothesis, right? And I'm gonna divide that by my standard error of the mean. Standard error of the mean, again, is gonna be my population standard deviation divided by the square root of my sample size, okay? And so essentially what we're working with here is gonna be a distribution of sample means, right? My distribution of sample means is gonna assume for all possible samples of 25, right? How much difference would I expect any randomly selected sample from this distribution to fall away from the mean, assuming that we've, again, pulled a random sample of 25 with a population standard deviation of 20, okay? And so if I get something that's very much different than that, right, we would say that this would be an unlikely sample to draw from a population with this characteristics. If it's close, then we say, yeah, it's not exactly 80, but this seems reasonable based on what we know about the distribution of our sample statistic based on this population here. Okay, so our z-test, again, is going to be a ratio between the difference, right? So if we take a look at this is going to be important. Most of our samplings or our statistics we work with this semester are going to follow this same pattern. In the numerator, we've got the difference between our sample and what we would expect under the null hypothesis, okay? In the denominator here, we have the expected distance between the sample mean and the population mean under the null hypothesis. So this is our observed difference. Our standard error, again, is telling us how much of a difference we would expect based on the number of people we have and the standard deviation in the population here. So we've got what we observed over what we would expect, assuming that there's nothing going on here, right? And as we go through, as the difference that we see starts to exceed the difference we would expect due to just random sampling, given our distribution of sample means, that's going to mean our test statistic goes up. And as our test statistic goes up, it's going to go farther out into the tails, increasing the likelihood of us rejecting the null hypothesis here. People kind of following the logic here with what we've got going on? Okay, so let's go through a couple of examples here. Let's say that we, what is the Z statistic if individuals taking antioxidant supplements scored an average of 92 points on the neurological assessment? So what's the first thing we need to do here? What's that? Okay, yeah. Yeah, do that. Okay. Drawing our distributions here, right? And we want to say, what's our cut point, Amanda? 1.96, negative 1.96, okay. All right. And so what do we need to first do before we can calculate our test statistic? Laura?
Calculate the standard error.
Standard error, perfect. Right, and here we're going to use standard error of the mean as this, given that we're using population values, right? And so we're saying that we have a population mean for this test of 20, or excuse me, population standard deviation of 20 divided by what? Square root of 25. Gives us a standard error of 4, correct? Perfect. All right. So then 92 minus 80 over 5 can give us what? I believe it. What is it? Or what's over 4? Yep, thank you.
And 3.
What is it? 3. Okay. So my cut point is 1.96, right? I've got a value of way out here. Nick, just looking at this, what is my assumption based on what I've collected here?
With your Z that far out, you would reject the null.
I would reject the null, right? Essentially what I'm saying is if the population, the average the average cognitive functioning score for older adults taking antioxidant supplements, if the average score in the population, it really is 80, right? And I've collected a good sample. An average score of 92 would be very unlikely for me to, it would be very unlikely for me to select a sample of 25 that has an average score of 92, assuming that the population, that the actual score in the population is 80. Okay? This would be way out of bounds, right? And probably, as Nick has said, we would reject the null hypothesis and say these data aren't consistent with an assumption that the average cognitive functioning score in older adults taking antioxidants is equal to 80. It looks like it's considerably higher, right? What's our best guess for the average cognitive functioning score in the population of older adults taking antioxidants, Amanda?
Well, for us, based on this sample data,
92, right? This is what we're thinking is our best guess of the true population average is 92, right? And that's a way distance off of 80 what we thought, right? So again, the difference that we saw is 12 points. The difference that we would expect just due to sampling differences, assuming that the true population value is 80, would be about 4 points with a sample of 25. We're way beyond that, right? So people kind of see how this all kind of ties in and how we start to make inferences based on this. Anybody have any questions? Don't lie to me. I know you do. I didn't explain it that well. Yes?
You just chose 1.96 because you were assuming our alpha is
0.05, yeah. And that's going to be standard unless I tell you different. I will to trick you, so make sure you're paying attention and stuff. But all right. What about, let's say we change the scenario up and we say, all right, instead of a sample instead of having our sample of 25 have an average score of 92, let's say it's 84, okay? Again, we go through our standard error here. It's going to be 20 over the square root of 5, or 25. It's going to be equal to 4, right? Now our z is going to be 84 minus 80 over 4 gives us a, z equals z. Gives us a z equal 1, right? In other words, z equal 1 following in our distribution here.
It's written.
Yeah, I'm going to be right in here somewhere, right? So here, right, relative to the last example, we're still getting, in our sample, is still demonstrating an average functioning score that exceeds what would be expected in the population, at least in terms of the point estimate, right? 84 is bigger than 80, right? I don't need a statistical test to tell me that, right? But is this difference larger than what I would expect under just based on basic sampling variance? And it's not. It's actually just right there at what we would expect, right? And so, Emilio, what would be our conclusion based on this scenario?
First, we failed to reject it, so we would assume that it's similar, if not the same as population.
Okay. Like 50% correct in general, but the error that was made here is one that's commonly made in null. If I find that if I fail to reject the null hypotheses, is that telling me that the average functioning score in the population of older adults taking antioxidant medications, does that say that their true population mean is 80? No, it's just saying that we can't say that it's not, right? I'm making no assumption or I'm drawing no conclusion about what the actual population parameter is. All I'm saying is I just don't have enough evidence to say that it's not, that it's different than what's assumed under the null, okay? And this starts to get tricky, right? This is something we all know or should know, but continually make problems for say, there's no difference in these populations. Well, I don't know that there's no difference. I'm just saying I don't have sufficient evidence to claim a difference, but whether or not there is a difference or not, I don't know, right? What would happen if instead of Emilio, if my sample wasn't 25, if it was 200?
Then the Z statistic would go.
My Z is going to go up through the roof, right?
So-
And so a lot of this depends on how much, like, so I can't say I can find this, still find the same absolute difference, but depending on my sample size, that difference might very much be very significant, or we might fail to reject the null hypothesis in this situation. Okay. For anybody who's done like correlational research, is a correlation of 0.2 statistically significant? What do you think, Layla?
A correlation?
Yeah, a correlation of 0.2.
Oh, 0.2.
Is that statistically significant?
No.
I don't know, it depends on how big the sample is, right? If I have a sample of 20, no. If I have a sample of 200, yeah, right? And so it really depends, and so this starts to get into some of the inner workings of our test statistics. And so all of this is just to say when we fail to reject the null hypotheses, what we're saying is we don't have enough evidence to claim a difference. I don't know, I'm not saying that there is a difference or there's not. I'm just saying that we don't have enough evidence to say that we have a reliably different, that it's likely that our population mean here is different than 80 or not, based on what we calculated. Yeah.
Is that how you would word it, that we failed to reject the null?
Yeah,
or would
and I'll
you
go.
say that?
Yeah, I'll go through and give you some examples of this. Okay. So scenario 1, here we have a mean of 92, alpha level 0.05, critical values plus or minus 1.96. We calculate our confidence interval, right? Then we're just taking 92 plus or minus 1.96 times our standard error of 4, right? Calculating our confidence interval here, right? Here's our value of 3, right? And so we would likely reject the null hypothesis here. Not likely we would, because it's exceeded our critical value. Here, we have an alpha level 0.05. Again, critical value is 1.96. Here, our confidence interval, lower bound, based on the data we've collected, lower bound estimate for the population, the mean average cognitive functioning in the population of individuals or older adults taking herbal supplements, lower bound of 76, upper bound of about 92, okay? Evelina, does our null mean of 80 fall within this confidence bound? It does, right? And so we would say, even based on this confidence interval, we would say, yeah, we don't have enough evidence to reject the null because 80 is a plausible value, right? It's kind of right there in the middle of it. It's a non-refuted value. It seems reasonable. That would be a reasonable guess based on the data that we've collected. But what we could do then is we could go through calculated test statistics z-score. We find it's hanging out, right? Or our z-score of 1 hanging in here doesn't exceed our critical value. And so we would fail to reject the null hypothesis here, saying that we don't have sufficient evidence to claim that antioxidant supplements have any impact on, have a clear impact on cognitive function. Yeah.
Would you also interpret the confidence interval when rejecting?
And this is what I'm going to have you do, and it's going to be, I'm going to have you all, as you're working through this, put a greater emphasis on the confidence intervals than your statistical tests. Just because I want you to be working with these, and this is just best practice statistical recommendations as you've seen from most of the articles I've had you read. And so what ends up happening in function is it ends up being redundant information. But that's fine. I want you to go through and make your primary assessment based on this. The one thing that you shouldn't be doing, and again, just burn this into your brain, your confidence interval is not giving you anything different than your statistical test. Your statistical test is not giving you any different information. You'll never have a disagreement between your statistical test and your confidence interval, right? Your confidence interval is never going to tell you one thing, and your statistical test or your hypothesis test is gonna tell you a different thing. They're always the same. Because what happens is sometimes people, when they write up the back, well, we found that confidence interval, lower bound estimate of 76, upper bound of 72, because null value of 80 falls in the middle of there. We find additional evidence based on our null hypotheses test. Urge, nope, not additional. It's the same information. You just say hypothesis test associated with p-value of whatever. We reject the null hypothesis, so on and so forth, right? So your statistical test isn't giving you any different information than your null test or than your interval estimate. Your interval estimate is just giving you a richer interpretation and more information about what's going on than just an up-down on your null hypothesis test. Okay. Other questions? All right. So then what we're going to do is we're going to draw a conclusion, right? We're going to draw a meaningful conclusion based on a range of possible population values, precision or point estimate. How precise is our point estimate in this example? Not great, right? I mean, it's fine, but it's still, right? We got 76 to 92 is pretty big, 84 to about 100. I mean, it's a pretty wide interval, right? But again, why are we getting sort of less precision on these interval estimates, Amanda?
Because we have a fairly small sample size.
You have a fairly small sample, right? Our standard error is quite big, and so it's adding more variability into this, right? So what we want to do is pull in information about from our confidence interval, upper and lower bound of population parameter, precision of our estimate, effect sizes, and size of effect based on our confidence intervals. We're going to talk about effect sizes down the road. We'll work all this in to make some sort of meaningful conclusion about the research question at hand, right? We're not just saying NHST reject, fail to reject. What does this tell us about the likely impact of antioxidant supplements on cognitive health in older adults, right? So wanting to pull all this together, okay? So our decision in terms of reject, fail to reject, we reject the null hypotheses when our sample statistics fall within the critical region, like sort of outside or more extreme than our critical values. This is going to suggest, as we talked before, that the sample data are unlikely, assuming that the null hypotheses and all assumptions of the statistical model are true. Okay, if we haven't violated our assumptions, right, we're suggesting that these data are unlikely if the actual population, the actual average cognitive score in the population of older adults taking herbal supplements, if it actually is 80, these data are very unlikely to be extreme this far. What we're going to do is we're going to conclude that our sample that we've got, likely drawn from a population with a mean that's different than that specified under the null, and we're in taking this as an indirect support for the null hypothesis, right? We're saying, all right, under our null assumption, this is kind of the distribution of scores that we should get. We found something that's way out here. Therefore, we're saying that these data are unlikely, assuming that the null hypothesis is true, right? We're assuming then, sort of making the inference then, that it's likely that the population value the value of the population parameter from the population that we pulled from is probably different than what was assumed under the null hypothesis. And we're using this as indirect support for our alternative hypotheses that, yes, antioxidant supplements likely have an impact on functioning, okay? So it's a lot of indirect stuff, right? We're just saying, here's what we would expect under the null. We got something way out here. So based on this, we're saying that it's unlikely, that these data are unlikely assuming the null, and so by the converse, we're saying that it then probably the parameter of the population from which this sample was drawn is different than what we were assuming, and so we're going to reject the null and implicitly say, so that's support for the alternative, okay? By contrast, if we fail to reject the null, is when a statistic falls within the body of the distribution, and again, suggesting sample data are plausible, assuming the null hypotheses, right? We didn't get, our mean value wasn't exactly what we'd assumed under the null, but the data that we did, it's within reasonable what we would expect, assuming, so from a population with a mean of this level, we're going to conclude that we have insignificant evidence to claim an effect, right? And again, this is agnostic versus atheist. We're not saying there is no effect. And we do this all the time. I'm guilty of it, right? Sometimes I've gotten called out by reviews on papers. It's embarrassing. Like, I'm going through, like, let's say, like 10% of people in my sample didn't fill out questionnaires, and so I kicked them out, right? And so I'm like, oh, so they didn't find differences in terms of people who completed or didn't based on X, Y, and Z. Therefore, there's no difference. Again, the reviewer comes through and like smack me, rightfully so. Right? Well, just says you didn't have enough evidence to say that there was a difference, right? So then I'm like, yeah, fair enough. And so then you gotta go through, change things around, right? So we're not saying that there's not an effect. We're just saying that we don't have enough evidence to say that there is an effect. This leaves us kind of in this place where we're saying, well, I don't know, maybe there is, maybe there isn't. I really can't say one way or the other, okay? Failure to reject does not prove that there's no effect. Okay, if I fail to reject the null hypotheses, this is not evidence that the effect is 0, or that the actual population value in the sample of older adults who use supplements is actually 80. It's just saying that we don't have enough evidence to say that it's not. Okay. Questions about this? This is very important when we're going through and making good, strong interpretations based on our data. All right. Wilkinson, never use the unfortunate phrase accept the null hypotheses, right? Someone will do it at some point, right? I'll be very upset, right? And I'll say, oh no, you didn't. That was, Tara came up with that. It was like Tara Cloud, 2018. She made me acknowledge that this wasn't my cool joke. I made the meme, but she, all right. So, thinking about how we tie this all together within a conclusion, okay? This based on, let's say that the example that we walked through was something I had on the problem set. This might be something that I would say, yeah, no, you did a nice job of pulling this together. So we say, for scenario 1, point estimate for the mean cognitive functioning population of older adults, take the antioxidant supplements, see what I've done there? I've identified that we're making inferences about a population, told you what we're measuring, identified the population here was 92, 95% confidence interval for these data suggests that values of 84.2, 99.8, reasonable lower and upper bound estimates for mean cognitive functioning in this population, right? So I've identified a point estimate, I've talked about lower and upper values, and keep reminding you that we're talking about not my sample, but a population of people who are interested in looking at. Probability of randomly selecting a sample of n equal 25 with an average functioning score of 92 or greater, assuming null hypothesis, assuming a true population value of 80 is 0.0013. Where did I get that? Someone have a Z table out on hand? So you got one. Find a Z-score of 3, and then tell me what the probability of finding a Z-score of 3 or greater is. What's up?
It's the smaller portion for
Yeah.
Z-score of 3.
Yeah, right. So we're saying that the probability, if I go through and use my Z-table, and I want to actually calculate the probability value, right, of obtaining a score. If the actual population value is 80, the likelihood of me randomly selecting a sample of with mean of 92 with a sample of 25, if I look and I go down through and I look at my Z table and find the probability associated with a value of 3 or greater, sort of in this piece right here, is very, very low, right? 0.003. So I'm going to ask you to go through and actually look at those probability values based on your Z's. Right, so you go through, take a look at your Z table, find sort of what your 3 or greater. It's going to be 0.0013. Score falls within the critical region or outside, however you want to say that, set by alpha 0.05. We reject the null hypotheses. Include the antioxidant supplements are associated with statistically reliable increase in cognitive functioning among the elderly. Okay, so what we're trying to do is come through, and so this doesn't have to be pages and pages. I don't need a thesis on this. What I want you to do is try and get used to and get flexibly, and able to flexibly go through and integrate this information into something that sort of is hitting this at different levels, right? So we've got confidence interval, we've got probability values, we've got reject the null hypotheses, so on and so forth, tying all the stuff that we've worked into this point to go through and give you a reasonable assessment of what we found and how this relates to the original question at hand. Okay. Questions with this? All right. Scenario 2, right? Different here is where we fail to reject. We would say supplement use in older adults associated with incremental increase in mean cognitive functioning relative to scores in the general population, right? So I'm saying it was an increase, right? We saw an absolute increase in the scores. However, confidence interval for this point estimate evidence considerable margin of error, plus or minus 7.8, with a deviation with population mean failing to meet benchmarks for a small effect. Don't worry about effect sizes yet. This is just kind of an example worked in. Say the probability of randomly selecting a sample with a mean cognitive functioning score of 84 or greater, assuming a population value of 80.1587. Again, where did we get that? What's that?
The smaller portion of your z-score.
Yeah, the smaller portion. So what's in the tail of 1 working over, right? So again, is a probability of 0.15 or 0.16, is it great? I don't know, I'm not happy about that probability if I'm sitting down at a poker table or something like that. But it's not super unlikely that I would do that just by chance, right? So we would say the score falls outside our critical region set by alpha 0.05. We failed to reject the null hypotheses given insufficient evidence claiming a reliable effect of antioxidant supplements on cognitive functioning in the elderly. Okay? So again, just taking a couple of different scenarios, and this isn't something that I want you to like cut and paste and just swap out stuff. Don't do that. I've had that problem in the past. People are like, oh, I thought that was stock language that I want you to use. Do not. There's no stock language. I want you to use your creative brains and sort of be able to tie this together into a way that communicates this information nicely. It's nice to have kind of an idea for what yours might look like, right? How to knit all this stuff together. But please do not copy and paste this, because then we'll have a discussion about you not doing your own work and using my work. I know I wrote that. I know what that looks like. I can do that, right? I want to see what you guys can do and pull this together, okay? Questions on how we integrate this together. So we're bringing in confidence intervals. We're talking about point estimates. We're talking about populations and expected values. We're talking about the probability of assuming that the null hypothesis is true, assuming that the population score in older adults using cognitive supplements is 80. What's the probability that I would randomly select a sample of 25 people with a score, with a standardized score at this level or greater, right? Pulling that in. Talking about failing to reject, and then drawing some meaningful conclusion about the question at hand. Functionally, is antioxidants helpful in terms of cognitive processing in older adults? Okay. Questions about this? All right, cool. And when we're going through this, in general, start with your confidence interval. Start with your interval estimate in your interpretations. This is going to help you sort of get good with that. And then when you get to the hypothesis test, that's just mostly a formal statement of reject, fail to reject, or sort of like test was associated with a p-value of whatever. Is really like once we go through and actually get your confidence interval talked about, there's really not much that your statistical test adds in outside of you just saying, and associated hypothesis tests associated with the p-value of this, or something like that. All right. We'll pick up with another example here next week when we start in. Any questions about anything up to this point? All right, we're doing pretty